Hello, good people. Welcome to this episode. So, we are continuing the trend where I pick very simple algorithms that I believe you will be able to understand based on what I've taught you so far. And these are algorithms that have real world applications that you can readily use. And I show you how to implement them and then when to apply them. So, the objective of today's video is to teach you about a very simple reinforcement learning algorithm called the multi-armed bandit algorithm. And the objective is to show you how to implement the different variants of it and how to understand how it works internally, and also to be able to identify situations under which you can apply the multi-armed bandit algorithm. After this video, we'll go back to our trend on deep learning, and what we'll be talking about is logistic regression, where we will learn how to classify data points into two classes, and we will apply it into a medical problem, and we also apply it in image classifications. So let's get started with multi-armed bandit. What is the multi-armed bandit algorithm? In a nutshell, the multi-armed bandit algorithm helps you to take optimal decisions under uncertainties. And to explain, I'm going to use the image you are seeing here to help you understand the need for the multi-armed bandit algorithm and how to implement them. Of course, we're going to write code to do that. Okay, so what you are seeing here are called slot machines, which are usually found in casinos. I got this image off the internet, thanks to whoever made it available. Now, in this picture, you have three machines, but in reality, it can be 10, it can be 20, it can be any number of machines. It definitely has to be a finite number of machines. It cannot be infinite, of course. Now, each of these machines have arms that can be pulled, okay? So this is arm, this is another arm, and this is the arm for the third machine. How they work is that they have configured these machines internally to have a different payout rate. So anytime you pull the arm of each of the machines, there is a probability of you getting a reward, and the reward is going to be in terms of money. So for example, they could configure the machine 1 to give you $10 with a probability of 90, like 0.9. So 90% of the time, if you pull this arm, you're going to get $10. It could also be that machine 2 has been configured to give you $100, but with a probability of 0.1, which is 10% of the time you can pull the arm and you might get $100 out of it. And the third one also has a different pay rate. The probability is different, and the amount that you get is also different. Now, the situation you find yourself in when you stand in front of these machines is that you don't have an infinite number of times for you to interact with a machine. It could be that, okay, you have 10 chances to pull the arms, and your objective is to maximize the amount of money you get as much as possible. So the question then is, without knowing the pay rate of these machines, how do you go about choosing the right arms? How do you go about deciding which arms to pull so that at the end of all the number of steps that you are allowed to interact with the machines, you would actually make a lot of money, the maximum amount of money possible? And this is just a casino example that I have used to explain to you. But in reality, there are a lot of scenarios where this situation matches something that you want to do in reality. For example, if you are building a platform for online advertisement and you want to know which adverts to show to users so that you can increase your click-through rate, this algorithm is applicable. If you are doing A/B testing where you have multiple features on your system and you want to turn them on or off, and then learn how people are going to use those features, you basically want to measure how people value those features so that you know where to exert your effort. This also becomes applicable, and particularly for me at work, I've been working on this for the past 2 weeks, and we are using Multi-Armed Bandit to personalize search results for people in a privacy preserving way. So anytime you have to take optimal decisions under uncertainties, remember that there is the multi-armed bandit algorithm here, which you can easily apply. And the good news is that it's an online learning system. By online learning, I don't mean it runs on the internet. That is far away from the truth. Online learning means it is a live learning system, it's a reinforcement learning system where the algorithm or the agent will be able to adapt to the changing needs of the situation. Okay, so the good news about such simple reinforcement learning algorithms is that we don't need to gather data beforehand, because the agent is going to interact with its environment, and then it is going to take the wisest decisions possible. Okay, so let's go ahead and get started. I'll explain and implement with you as time progresses. So I'm going to import NumPy as always, and I'm going to import matplotlib.pyplot as plt, and I'll do matplotlib inline. Okay. What? No module named matplotlib. Okay, I didn't spell pyplot correctly. Okay, so now we have all the import, and as you can see, everything here are modules that you know about. And I'm going to paste a function that I've already created. This is not the objective of the video, so I will not explain this function to you, but basically it's going to help me to plot the history of the agent interaction with the environment, so that we will know how well the agent is performing. If you know matplotlib already, you should be able to understand this. If you do not know matplotlib already, I suggest that you watch my matplotlib playlist on my YouTube channel, where I teach the basics of matplotlib for people who are learning from me, so that you don't get lost. Okay, so the first thing we need to do is we need to create an environment. Okay, and then we will set the probability of payout, and then we also set how much the environment actually pays out. Okay, I'm going to use code to explain, so follow me here. So I'm going to create a class called env, and then in its constructor, underscore self, I will take reward probabilities. You will understand this. I'll take reward probabilities, so I'll call it reward probes, and then the actual rewards. Okay, don't worry if you don't understand up until this point. I am going to instantiate an instance of it, and then you definitely understand what's going on here. Okay, so the reason why the algorithm is called multi-armed bandit is because it can have a lot of options for the agent to choose from. So in our implementation of the environment, we also want to know how many arms are available. Okay, so the reward probabilities is going to be a list of probabilities with which each arm is going to reward you, and the rewards is also a list of the actual rewards that you get from each arm. Okay, and so the first check we want to make is that we want to make sure the length of the reward probabilities and the length of our rewards are equal. Otherwise, we throw an exception because the environment is invalid in that case. So we check if length of reward probes is not equal to the length of the rewards. Then what we do is we are going to raise an exception. So we basically throw an exception, and what the exception is going to say is size of reward probes or probabilities. Then I'm going to show the actual size, so that if you see such an error message, you know where the problem is coming from. So reward probes, I'll say does not match size of rewards, and I'm going to show the length of those the rewards list as well. Okay, so we throw an error if this condition is met. Otherwise, the environment reward probes is equal to whatever reward probabilities you pass it, and then the rewards is equal to whatever rewards you've passed it. And now the environment should know how many arms it has, how many arms are available. So I'll say I'll call that K arms. So if the arms is 3, then it is a multi-armed bandit which is dealing with 3 arms. If it is 10, then it's a multi-armed bandit which is dealing with 10 arms. And because we have already checked to ensure that the reward probabilities and the reward list have the same length, we can choose the length of any one of them to represent the number of options that are available to the agent. Okay, great. Now we have this class created. Don't worry at this stage. I am going to create an instance and then I'll use it to explain how we will build an agent to interact with this environment. So I'm going to create a function called chooseArm, and then it is going to take an arm. So in this case, if our K arms is 10, then our agent has the option of choosing an arm between 0 and 9, because if you count from 0 and 9, you actually get 10 options. Okay, so what we do here is if we also check if arm is less than 0. So because the arm count start from 0 to K arms, we don't want you to specify any arm that is less than 0 or any arm that is greater than K arms. Okay, so if there are 10 arms, you shouldn't be able to choose the 10th. You shouldn't be able to specify 10 as the arm. The 10th arm is a 9. It has a value of 9. I mean, this is basic counting principles in every programming language. I think I'm explaining too much. Okay, so over here what we do is I'm going to use an f string here, and I will say arm must be a value between 0 and 0 and self.karms minus 1, because I mean I've explained this already. Okay, so if you specify any arm that is not valid, we throw an exception. Otherwise, we return self.rewards arm if np.random, I will explain this, is less than self.rewards reward probabilities for that arm, else we return 0. Okay, so now it's time for me to explain. I have this function called chooseArm, where you can specify the arm. That is basically specifying the arm that you want to pull on the multi-armed bandit. In this case, in this image, you want to specify the arm of which machine you want to pull. Okay, so what we do is, you see, in the creation of the class, we stated that we have reward probabilities and we have actual rewards. So the reward probability says that, okay, for machine 1, it has 50% chance of giving you a reward. And the rewards list actually states how much it is actually going to give you for each of these arms. Okay, so what we do here is, because each arm or each machine is internally guided by a reward rate, what we do is we generate any random number, and if that random number is less than the reward probability of that particular arm, okay, then we give you the reward for that arm as stated in the rewards list. Otherwise, we give you 0. Okay, so we have created our class. Let's go ahead and create an example. This will make it much more concrete. Okay, so I'm going to create environment. I'll say it's equal to env, and then I'm going to specify my reward probability. So over here, let's say the first arm has a 0.01 probability of giving you a reward. Okay, and I'm also going to specify the rewards over here, and I'm going to do it side by side so you understand. So 95.0. okay, so what this means is that the first arm has a probability of 0.01 chances of giving you 95. This could be money or anything. Okay, and then we come to the second arm. I'm going to put in 6 arms here. Feel free to change it to any number of arms that you want. So let's say the second arm, 100% of the time, it is going to give you 0. That means regardless of how many times you pull that arm, you will always get 0. Okay, now let's come to the third arm. We come to the third arm, and the third arm has 75% chance of giving you, let's say, 25.5. okay, and let's go to the fourth arm. The fourth arm has 99% chance of giving you let's say 10.05. These are arbitrary numbers that I'm choosing, and the objective is, at the end of the day, the agent that we build should be able to make the wisest decision possible. So the next arm has 65% chance of giving you 5.45, and let me add the last arm. The last arm has 100% chance of giving you 2.50. Okay, so now we have our environment created. Let's print out certain things from the environment that will make things a bit clear for us. So reward probabilities, I mean, these are the things that we have already specified, but I'm going ahead to show it here. I just want to leave two tabs, and then I'll show environment dot reward probes, and I'm going to do the same for the actual rewards so that we can look at them one after the other. So I have the rewards over here, and this is supposed to be rewards. Okay, so let's see. Yeah, so great. What we have here is that we have 1, 2, 3, 4, 5, 6 arms, and the first arm has 0.01 probability of giving you 95. So you see, the reward you get here can be very large. In fact, it is the largest you can get out of all the rewards. However, the probability is so low, it doesn't make sense to be making this choice, because come to think of it, it is 0.01 is 1 out of 100. So you have 1 out of 100 chances to get 95. The next one definitely is always going to give you 0. No matter how many times you pull it, it's going to give you 0. Okay, the next one has 75% chance of giving you 25. So if you look at all the rewards here, it is the second largest, but the probability of getting that is a bit smaller than I mean the 1.0, which always gives you 0. However, 75% of the time it is going to give you 25.5. And this has 99% of the time it is going to give you 10.05. So the dilemma you face is, between these two options, which one should you be pulling often? And how do you even learn the probabilities? Don't forget that we have created this environment, so we have stated the probabilities of rewards in there. But in reality, you do not know. And that is why we need to build an agent that is going to automatically learn this pay rate, and also learn how to take optimal actions under such uncertain conditions. The next one, 65% of the time, 5.45. The next one, 100% of the time, is going to give you 2.5. Okay, so now let's try. Let's try to pull some of the arms for a certain number of times. Okay, so over here I'm going to say environment. I'm using list comprehension, so I'll say choose arm. Let's say I'm going to choose the arm that has 100% probability of always giving you 0, which is arm 1. Okay, so I'm going to choose arm 1, and I'm going to do that 10 times. So for I in range 10. Okay, so let's see. So see, we pulled it 10 times, and the reward we got were 0 all the time, because the distribution, or the pay rate, or the probability of reward is 100, and the actual reward is 0, which means if we pull this 100 times, we will always get 0. That is what this line here ensures that our environment is doing. Let's try another one. So this one, the first arm, which is arm 0, has 0.01 probability of giving us 95. Let's try it anyway. I mean, it doesn't mean it's impossible. It means that it's hard to come by. Sorry, I didn't change the right thing. So this is 10, and then let's pull 0. So let's see. So as you can see, we pulled it 10 times, we didn't get our 95 because of the probability. We try it again, we don't get it. We try it again, we are not getting it. We try it again, we are not getting it. So it actually goes to validate the fact that yes, the reward is big, but it's actually hard for you to actually get that reward. Let's increase that to 100 and see if we will ever get the 95. It doesn't appear like we got a 95. So as you can see, it will be a waste of time for you to keep pulling this arm in anticipation of 95, which might never happen. And this is what the agent is supposed to be able to learn automatically. Okay, now we have created our environment. The next thing we want to do is to build an agent. But before we will build different variants of the agent, the intelligent agent. But before we go ahead to build any intelligent agent, we need a base agent whose performance will form the base case that we will compare the performance of the other agent, and then we know that, oh, this agent is doing better than the other. Now, if you stand by such a machine in a casino, the least you can do, if you don't see the need to learn the pay rates, then the least you can do is to pull these arms randomly. Okay, you don't care, you just pull them randomly and you hope that you make some money out of these machines. So let's create an agent that behaves randomly. Okay, what I'm going to do here is I'm going to create a class called random agent. And the random agent is going to interact with the environment that we have created. Okay, so we have our usual init, which takes an environment, and then we also specify max iterations. So the max iterations, I'm going to default it to 2000. What the max iteration does is it specifies how many time steps the agent is allowed to interact with the environment. So what it means is within these 2000 iterations, we want the agent to make the most cumulative reward it can, as much as possible. Okay, all right. So self.env, we set it so you pass an instance of the environment to your agent, and it has to interact with that. And then I'll say iterations is equal to max iterations. Okay, now let's create the function that will let the agent act within the environment. So we have the act function, and this is what is going to let the agent interact with the environment and hopefully take the wisest decision that it can take. And because we are after the most optimal decision, we need to find a way of taking that optimal decision. And the question is, how do we go about taking this optimal decision? Think about it for a while, so that before we start implementing an intelligent agent, you have an idea how will you go about solving such a problem where you have to optimize cumulative reward under uncertainties. And learn, just think about it for a moment, and then I will also show you how to solve that. But in this particular agent, we want the agent to behave randomly. So we don't care. The agent doesn't really care. He's not interested in learning any useful thing from the environment. It is just behaving randomly. So what we are going to do is we want to actually keep track of the rewards that the agent is going to make, and then which arms it is also pulling. Okay, so I'm going to create a list called arm count. So the arm count is going to store which arm the agent decides to pull on each time step. Okay, or sorry, on each time step. So we want to know how many times the agent is pulling each of the arms. And so this is going to be, we are going to initialize it to zeros, np.zeros, self.env.k arms. Okay, so because this environment has 6 arms, our arm count list also has 6 entries. And what we are going to do is anytime the agent pulls a particular arm, we will increase that arm count by 1. When we finish, we want to plot a histogram to see which arm the agent pulled most of the time, and we will try to see if it even makes sense that the agent pulled those arms most of the time. And the next thing we want to do is we also are interested in the actual rewards that the agent is making. So we are going to create a list that is going to store all the rewards that the agent makes on each time step. And we also are interested in the cumulative or the average reward. I mean, the best term here will be average, but I'm calling it cumulative rewards. So it's going to be the average of all the rewards that the agent is getting over time. And if it is a wise agent, we expect that the average reward should be increasing with time. Okay. All right. So now we have these two lists created. Let's do for I in range. So we start from 1 to self dot iterations, which is the number of times it is allowed, plus 1, because we are counting from 1. If we started from 0, then we don't need to add plus 1, but we are counting from 1, so we add 1 to it. Okay, now this agent here is not a very wise agent. It just does things randomly. So to pull an arm, I'm going to say the arm is going to be np.random.choice. So we're going to make a random choice out of the number of arms available. So sorry, k arms. Okay, so we're going to pull the arm randomly. So the agent doesn't think, it doesn't even do any calculation. It just decides that I have k arms to pull from, and so I'm just going to choose an arm randomly, and that is what the np.random.choice does. So if you say np.random.choice and you give it a value of say 5, what it means is that if you make a random choice of any number between 0 and 1 less than the number that you have stated in there. Okay, so now we have chosen the arm randomly, and the next thing is we want to see how much reward we got for choosing that arm. So you say self.env.chooseArm, and don't forget that the chooseArm function returns a reward. That is what we return here. It returns a reward based on the reward value list that we supplied to the environment. So the reward is going to be self.env.chooseArm. Okay, so now we have the reward. What do we do? What we do is we're going to increase the arm count. We want to know how many times that arm has been selected. Okay, and so what we're going to do is we say arm count. So arm count for that particular arm plus is equal to 1. We bump it up. Okay, and then we are also going to say rewards dot append the reward that we got for choosing that arm in this particular time step. And the cumulative rewards is just going to we're going to append the average of all the rewards we have made so far. Okay, so it's going to be the sum of our rewards divided by the length of our rewards. Okay, and so at the end of the timestamp, I'm going to return a dictionary, and this dictionary is going to be used by the plotting function I created above. So it requires the arms to store the arm count, and we also are interested in the actual rewards that we made over time. So this stores our rewards, and then we also have cumulative rewards, which also stores our cumulative rewards. Okay, so now we have our random agent created here. Let's create an instance and let's see how the random agent behaves. So I'll say random agent is equal to random agent, and the environment is going to be the environment instance that we already created above, and the max iterations, by default it is 2000, but I'm stating it here so that just in case we ever want to change it, we can easily change it. Okay, now let's say random agent history. So I'll say random agent history is equal to random agent dot act. Sorry. So let this random agent act in the environment, and once it is done, we want to know the total rewards that it made. So I'm going to say print. I'm going to use f strings. I'll say total rewards or total reward. Yeah, total reward is going to just be the sum of, the act function returns the history, which is a dictionary. So we just want to sum up the rewards list out of the dictionary. So what we do is we get that out of this dictionary, and then we sum it. That is going to be the total rewards that our agent made after acting. So let's run this and see. Invalid syntax. So what could be wrong here? I said this is equal to sum. So find the sum of rewards. Okay, because I'm using f strings, I can't have two quotes. I have to use one, and then the other one should be two. Okay, all right, great. So we can see that after 2000 interactions with the environment we created here, our agents made a total reward of 12,630.23. So I mean, we can't tell which arms it pulled unless we make a plot of it. And that is why I started off by creating this plot history function. You basically give it the dictionary that the act function returns, and it is going to plot the average rewards and also the arms count, like how many times each arm was pulled. So let's call plot history, and let's give it array history. So we want to see what actually went on in our random agent's behavior. So you can see that yes, our agent saw six arms, 0, 1, 2, 3, 4, 5, and so that makes it 6. And of course, it obviously behaved randomly. You can see that it chose each arm almost the same number of times. I mean, they are all hovering between 300 and 350 times. Okay, so it means that it chose the 0 arm 300 times. It chose the arm 1 almost 330. It chose arm 2 almost 350. Arm 3, arm 4, arm 5. So like it was basically behaving random, and that is why you can see that there were times it was fortunate, and then it made some big reward, and then because it's behaving random, there is no general pattern in the behavior of this agent. But at least it gives us a base case. So what it means is that if you were given if we had a multi-armed bandit or a slot machine with this configuration, where the top ones are the pay rate and the second list is actually how much money you get out of those machines, and you behaved randomly the same way this agent behaved, then the maximum money that you can leave with at the end of your 2000 interactions is 12,630. Of course, there is randomness in here, so if we run it multiple times, we are not going to get the same value. So at this point you can see that yes, it was averaging between, I mean, it was making an average of about 6.3 whatever currency you are using for each arm that it pulls. Meanwhile, you can see that there are big rewards that it could have got. There are times it can make 25, there are times it should be able to make 10. And so if it is hovering around 6, then the average is too small, and it obviously means the agent is not intelligent enough. Let's run it one more time, and you can see that the total reward is always hovering around 11,000, 12,000, and it is almost pulling all the arms randomly. Okay, all right, great. So now at least we have a base case with which we are going to be able to compare the intelligent agents that we build. Okay, great. So the first intelligent agent that we are going to build is called the Epsilon Greedy agent. What the Epsilon Greedy agent does is, let me go to this image and explain things one more time. So you are faced with this situation where you know that these machines have some configured pay rates which are unbeknownst to you. Now the question is, how do you make sure you make the most money at the end of the number of times it's allowed for you to interact with this machine? And one thing you have seen so far is you can behave randomly just as the random agent has behaved, and you can see that the performance is quite abysmal. Great. What we can do, an intelligent approach is, one, don't forget that the probability distributions that we have here is not known to you. We had to create this simulation environment so that we can measure the performance of our agents. Okay, so it is unbeknownst to you. So the first thing you want to do is you want to explore. And exploration means you are trying random actions, and then you want to keep track of how much each machine is paying you. Okay, so if I pull machine 1 5 times and I get a total of, let's say, 15, and if I pull machine 2 5 times and I get a total of, let's say, 2. I pull machine 3 5 times and I get a total of 100. By common sense, I get to know that maybe I should keep pulling machine 3 because I pull them the same number of times and I'm getting the most amount of money by pulling machine 3. Now, the question is, you have to explore, okay? But don't forget, you have a limited number of times to interact with this environment. So you cannot explore all the way throughout. There is a point where you need to stop and exploit what you have learned. And exploitation means taking the best action so far based on what you have learned from your interaction with the environment. And exploration means give yourself the option, because I mean, if there are 10 arms and then you've been playing with just 3, what happens if the 7th arm is actually the true one that pays you the most? So what the Epsilon Greedy algorithm helps us to do is it helps us to solve one of the commonest situations in reinforcement learning, which is called the exploration exploitation dilemma, where you need to keep a balance between exploring and exploiting. And so the Epsilon Greedy algorithm exploits the environment at a certain rate, and it also explores at a certain rate. And there is another variant of it where we decay the rate, but for now we are just going to talk about the Epsilon Greedy, and then we talk about the Epsilon Greedy decay afterwards. So let's create our Epsilon Greedy. So Epsilon Greedy agent, and that is also going to take an object. Okay, great. Sorry, come here. All right. Okay, so let's create our initializer or our constructor, and it also takes the environment, it also takes max iterations. Let's default this to also 2000, and let's call this epsilon. Okay, so I'm going to set epsilon to 0.1, and I'll explain to you what this epsilon function, this epsilon parameter does. Okay, so let's come in here and say self.env is equal to env self.iterations is equal to max iterations, sorry, and we say self.epsilon is equal to epsilon. Okay, great. So this is all we have to do in our constructor, and let's come here and create our act function, and this is where I'll do a lot of the explanations that are specific to Epsilon Greedy. Okay, so when I went back to use this image to explain to you how you can balance exploration and exploitation, I said you need to keep track of the payout or the pay rate of each of the machines, and the way we do that is to calculate something we call the Q values. The Q values is just basically telling you the pay rate of each of the arms. Okay, so let's start by initializing our Q values to be equal to numpy.zeros, and then it has to be the number of arms that are available, so K arms. Okay, so we start off by saying, okay, because we are starting afresh, we assume that the pay rate for each of the arms are 0. Okay, and we also want to keep track of the total rewards that we are getting from each arm, so I'm going to call that arm rewards. So arm rewards is also going to be np.zeros. In fact, I can just copy this because we use it a number of times, so I'll just copy this and paste it here. And we also want to keep track of how many times each of the arms have been pulled, the same way we did for the random agent. So arm count is also going to be equal to what we have. Okay, great. And then let's go to our rewards, just as we did for the random agent, and then we also do our cumulative rewards, which is also similar to what we did for the random agent. Now, the smartness of the Epsilon Greedy algorithm is this. I have this parameter here, epsilon, that I have set to 0.01, which means 1 out of 100. Now, the way the Epsilon Greedy algorithm works is that for epsilon with epsilon probability, it explores, and with 1 minus epsilon probability, it exploits. So what it means here by setting my epsilon to 0.01 is that out of every 100 time steps, my agent will decide to take a random action instead of taking the wisest action that it knows so far. And the reason why this is important is the wisest action or the best arm that the agent might have known so far might not really be the best arm in reality. It could be that if it explores more, it would identify another arm that is better than what it knows now. But because we have limited time steps to interact with the environment, we don't want to spend all our time exploring. Otherwise, we consume all the time steps, and we will not make the most amount of rewards that is possible for us to make. And so we explore epsilon. We explore with epsilon probability or epsilon number of times, and then 1 minus epsilon probability we exploit. Okay, so the way we do this is inside our for loop. Okay, so we do for I in range 1 to solve dot iterations, think plus 1, I guess. Yeah, what we do is we say the arm that we want to choose is, I'm going to write this code and I'll explain to you. np.random.choice. So we make a random choice from solve.env.k arms, just as the random agent was doing. If np.random.random is less than solve.epsilon, else np.argmax q values. Okay, great. So I know this line might be tough for you to understand, and so I'm going to take my time to explain it here. So what is actually happening here is, for the Epsilon Greedy agent, the way it chooses the arm to pull is, first of all, it is going to generate a random number. This is just one line that is doing an if-else statement. This is the beauty of Python. So it is first of all going to generate a random number, and if the random number is less than epsilon, then it means we want to explore. However, if the random number is greater or equal to epsilon, then we want to take the action that has the maximum value. And mind you, the Q values we haven't calculated yet. For now, they are zeros when the agent is starting afresh. But the way we calculate the Q values is that we just want to find the average payout rate of each of the arms. And so if the random number generated is greater than epsilon, then we want to take the argmax. The argmax of any numpy array, like I explained to you some videos ago, is going to return the index of Q values where the value is the highest. Okay, so all that this line is doing is that generate a random number and check if the random number is less than epsilon, then take a random action. Otherwise, take the action with the maximum Q value. Okay, so now we have taken the action. We don't know whether it's going to exploit or explore. It depends on the random number that is generated, but we are still interested in the reward we get, because for each time step we get a reward. Okay, so solve.env.choose, we choose the arm. I'm sorry, env.choose arm, choose arm, and then we specify the arm that we want. And the next thing we want to do is we say arm rewards. So we are going to increase the total rewards we have obtained by pulling that particular arm. So we add reward to that. Don't forget that this is the array up here. And we do the same for the arm count. So arm count for that particular arm, we do plus equals 1, because we want to indicate that we have chosen this X number of times. Now we use the arm rewards and the arm count to evaluate the Q value for that particular arm. So we say Q values for that particular arm is going to be equal to the arm rewards for that arm, which is the total rewards we have obtained by pulling that particular arm, we divide it by the number of times we have pulled that arm. Okay, and this is going to give us the Q value for that particular arm. So it's an estimate of how valuable that particular arm is to us, or in this particular case to our agent. At this point, everything else is similar to what we had in the random agent. So we bump up our rewards, and so we basically bump up our rewards, and we calculate the cumulative reward as well. So rewards that append the reward, and then cumulative reward is going to be the average, and we are going to return the same dictionary so that we will be able to plot it with the same function. Okay, so we come down here, and what we do is, I want to make sure I get my indentation right. So this, and yes, that should be it. Okay, great. So let's run this cell, and let's create an instance of the Epsilon Greedy algorithm. So e-greedy agent is going to be equal to epsilon greedy agent, and it's also going to interact with the same environment. It is important that they use the same environment because the random agent is the base case and it uses the environment. So for us to evaluate the performance of this, we also have to make sure the number of iterations is the same. And over here, I'm going to set epsilon to be equal to 0.1. So what it actually means is that in the definition of the class, I said it should explore 1 out of 100 times, but in reality, I want to explore 1 out of 10 times because I wanted to explore early enough and then figure out the best out there. So I'll say epsilon greedy history is equal to e-greedy agent dot act. So let's make our agent act, and we're also going to print out the total reward just the same way we did over here. So I'm going to come down here, and instead of RA history, I'm going to use EG history, and everything else should be the same. So see something, you can see that with the same number of iterations, the Epsilon Greedy algorithm is making 35,927, almost 36,000. Let's see what the random agent made. It made, let's say 12,000. So if you behave randomly, you can live with something as little as 12,000. But if you behave the way the Epsilon Greedy agent is behaving, where you reserve a certain probability to exploit and you reserve a certain probability to explore, then this is what you actually end up with. So let's go ahead and then plot. This is the beauty of the Epsilon Greedy algorithm. You can see that it will settle on a particular arm once it has learned enough of the action values. So let's see. Good. So you can see that, see the average reward for the Epsilon Greedy algorithm. You can see that the average reward for the Epsilon Greedy algorithm was hovering around 17.5. And from the plot of the arms count, you can see that it pulled the second arm more than it pulled any of the other arms. Okay. And if we come here and we inspect, by inspection, we can see that even simple common sense tells us that if arm 2 has 75% probability of giving me 25, then I might as well pull it more times than arm 3, which has 99% of the time, but it will give me only 10. Okay, so yes, it is rest assured most of the time I'll get 10, but over here 75% of the time is not so bad and I get 25. So if I fail twice and I make it the next one, I'm actually making something close to what I'll get by pulling three times and always succeeding. So this is the beauty of the Epsilon Greedy algorithm, and you can see that the Epsilon Greedy algorithm has figured over time which arm rewards it the most, and you can see that it pulled arm 2 almost 1,750 times, like more than 1,750 times, and it pulled the other arms lesser. You can see that arm 0, it also looked promising because arm 0 gives you 95 but the probability is 0.01. And so at a point, the agent will be like, let me try this out. So it tries it out and it sees that, dude, the reward rate is not as great as it sounds. And so it resolves to using 2. And so you can see that this simple algorithm has helped us to be able to figure out the best arm, in this case, the best decision to make in a very uncertain situation. Let's go ahead and then talk about another variant of Epsilon Greedy, which is Epsilon Greedy with Decay. Okay, and what the Epsilon Greedy with Decay does is um, it reduces the probability of exploration over time, because once you have learned enough action values, you don't want to keep exploring. There is a time when you should feel okay, you have explored enough and you know the best arm to choose, and so you have to reduce your exploration rate. Otherwise, you waste times or time step that you should use for exploitation in exploring, and it is going to limit how much you make. Okay, so how we do that change is we are going to introduce a decay constant. So I'll call it decay, and a decay should be a number between 0 and 1. I'm going to set it to 0.01 by default, and a decay interval. So after every decay interval time steps, you want to decay epsilon. Okay, so decay interval, I'm going to set it to 50. So down here, what we do is, after we have evaluated everything, the next thing we do is, if I mod self.decay interval, and that means I need to set decay and decay interval here. So self.decay is equal to decay, and then self.decay interval is equal to decay interval. Okay, great. So what we do is, if the iteration mod the decay interval, so if it has gone decay interval time steps, okay, then we want to say self.epsilon is equal to self.epsilon multiplied by self.decay. Okay, so what's going to happen is, after each decay interval time step, we multiply our epsilon by a smaller number, which makes epsilon even smaller, so that the rate at which our agent explores is going to be less. And mind you, because of the introduction of the decay and the decay interval, blah blah blah, it is going to introduce some stochasticity in here, because our exploration rate is going to reduce, but generally it should behave better than the normal Epsilon Greedy algorithm. So I'm creating this, and then to make sure that our Epsilon Greedy agent here is not decaying, what I can do is, I will say I'll set my decay to be equal to 1. So if I multiply my epsilon by 1, it is still the same epsilon, and so it's not going to decay over time. And you can see that we still are doing well, and our agent is still hovering around the 17.5. And you see, it learns faster, about the 300th iteration, and then the agent is already approaching a very good average reward, and it has also figured out that arm 2 is the best arm for us to pull. Now let's create this agent again. This time we are going to use a decay, so that it's going to decay over time, and let's see how that also influences it. So I'm going to call this greedy decay agent, and so epsilon greedy and max iteration 2000 epsilon this, and I'm going to decay with 0.1. so after every 50 time steps, I'm going to multiply my epsilon by 0.1, which means epsilon should become even smaller. Okay, and I'm going to call this epsilon greedy with decay history, and I'm going to call this .act. Okay, and my history should also be epsilon greedy with decay history, blah blah blah. Let's do, okay, so you can see now with the introduction of the decay, you see that it is performing less. What it means is that the decay is having an effect on how well our agent is behaving. It means it stops exploring. Probably it stops exploring too early. Let's plot the history, and let's see which arm it settles on. But obviously it's not the best arm that it has settled on, and I'll show you how to fix this issue. So let's see what arm it settles on. See, so it has settled on arm 5, and let's see what arm 5 does. So arm 5, which is the last one, has 100% rate of giving you 2.5. So you see, it stopped exploring so early when it figured out that okay, this arm has 100% pay rate and it gives me 2.5. It settled there because we multiply epsilon by the decay, and the epsilon has actually decayed, because if you multiply a number between 0 and 1 by another number between 0 and 1, you're actually making the result lesser. Okay, what it means, however, is we can run this multiple times and we get different results. You see, now in this case, it is even behaving better than the original Epsilon Greedy. See, so Epsilon Greedy made 35,000. We ran our Epsilon Greedy with decay one more time, and now it is generating 38,000, almost 400. So it is making almost 3,000 extra rewards, more than what the vanilla Epsilon Greedy algorithm is making. Also, let's see, you can see that yes, they both settled on choosing AM2 as the best action, but you can see that the Epsilon Greedy with decay algorithm didn't waste a lot of time pulling certain arms. So you can see that it didn't even pull AM4 and AM5 at all. It just explored enough, and it figured out that 2 is the best arm to pull, and so it pulled it. Now, the reason why you run the Epsilon Greedy with decay several times and you get different result is epsilon and the decay is they become hyperparameters that you need to tune. So you have to play with it based on the problem that you are trying to solve. You have to play with it and then come up with the best epsilon and the epsilon decay value for your particular situation. So there's no magic formula for that, but mostly you don't want to explore too much, and you also don't want to decay it too fast, so that it is not going to behave as you expect. So let's say we decay it, let's say slowly. So yeah, it's still making 38, and it's still settling for it, which is not too bad. So you always have to play with it until, so now it is performing poorly. Probably the decay is making the epsilon to grow smaller over time, and we still have our 38,000. So this introduces hyperparameters that you need to tune for your particular situation, but you can see that generally it is learning a good way to take optimum decision under uncertain conditions. So there are a lot more variant of this algorithm that I can be talking about with you. There is Thompson sampling, and there is also Softmax Exploration, which I will leave to you as assignment, and I'll be glad if any one of you can do this and share with the rest of us in comments. And so thank you very much for watching, and in case you are wondering where you apply this Epsilon Greedy algorithm, trust me, it is out there, and it is running businesses, especially in the advertisement state. There is also application of this in clinical trials of medication. So you have new medicines that have been developed, like these vaccines that everybody is looking for to help treat corona or to prevent corona. The question is, how do we choose which vaccine is the best vaccine to use? And an algorithm as simple as this. So the way it works is you choose the vaccine randomly, you inject it with somebody, and then the reward is going to be a measure of the person's well-being, how well the vaccine helps the immune system to fight the virus. And so if you have 3 of them, you choose you choose to explore and exploit. Okay, because this is human life involved, so you don't explore all the time, which means if you explore wrongly, you kill a lot of people. And if you exploit too early and you don't explore, you might use the suboptimal drug for people when there is actually the better drug out there. And so this algorithm is very simple to implement. You didn't have to do with neural networks, you didn't have to do back propagation. It's just simple mathematics, and we are able to train an intelligent agent that takes optimal actions under uncertain conditions. And so thank you very much for watching, and if you haven't subscribed, don't forget to subscribe and leave your questions and confusions in the comment. I will attend to them. I'll see you in the next video when we talk about logistic regression and we apply it to problems in the medical domain, and also image classification, where we try to fit a photo into 2 classes by building a logistic regression model from scratch. So thank you very much for watching. I will see you in the next episode.